Hello everyone, welcome back to Bytes of CSE. So this lecture is about AVL tree. Now AVL tree is a subset of binary tree, and in fact this lecture is a continuation of the binary tree lecture which I've already uploaded in this channel. So the question is, why did we need this binary tree or this special binary tree? So there was a problem with a binary tree which I'm going to show you right now. Say you are given a list of values like this and you are to create a binary tree from these values. Now if you remember, when we tackle a problem like this, we scan the values from left to right and accordingly we create the tree. So the first value that we encounter is 1. So we create a node which becomes a root node. The next value is 2, which is greater than 1. Hence 2 is inserted as a right child. The next value is 4, which is greater than both 1 and 2, and hence 4 becomes a right child of 2. And similarly 6 becomes a right child of 4, and 7 becomes a right child of 6. Now what does this data structure remind you of? Well, a linked list, right? But this is technically a binary tree where all the left child pointers are contain null values. And the problem with this kind of structure is, though binary tree technically it promised that it will take like O log n time to reach any node if there are n nodes, in total nodes in a binary tree, but if you are to deal with this kind of a tree, it will take O n time to reach any node. Suppose this node number 7. Now this is a very poor data structure from that point of view, because it is more complex to insert in a binary tree than a list or an array, yet it is acting like a list. So what change do we bring about to this data structure so that this still becomes behaves like a binary tree? So the change that was mentioned was, let us impose a condition that the heights of the left and the right subtrees of every node differ by at most 1. So this, when a binary tree obeys this kind of a condition, that binary tree is known as the AVL tree. So going by this, suppose you have a tree like this and this. So the right subtree has a height of 2, that is 1 and 2, and the left subtree also has a height of 1 and 2, that is this. So the difference of height between the left subtree and the right subtree is 0. So this binary tree is an AVL tree. Now suppose you have a tree structure like this, this and this. Now the left subtree has a height of 1 and the right subtree height is 2, and the difference between the subtrees is 1, therefore at most by 1, therefore this is also an AVL tree. But now say you add another node here at this point. Now the height of the tree becomes 3 and this is 1, and therefore the difference in height is now 2, therefore this is no longer a AVL tree. It is a binary tree of course, but no longer an AVL tree. So now I hope you understand how to find out if a given tree structure is a AVL tree or not. So now let's see what do we do to actually height balance the structure, because see, you can't the order of insertion is the same as a binary tree, but now what is the change that we need to bring about in order to make a binary tree into an AVL tree? Suppose you have a rope like this is these are the two ends of a rope. So you are holding it by your hand at this position, and somebody says that make sure that both the sides are of the same height, and you will not be given any extra rope or any extra thread to make the heights similar. So what will you do? You will naturally pull this part down, and as a result this part will be lifted up and you get a structure like this. So you are holding here, so you get a structure like this. So this pulling down and this side being pushed up, this is known as rotation in AVL tree. So now suppose your binary tree looks somewhat like this. So this is not an AVL tree because the left subtree has a height of 0 and this has a height of 2. So naturally you will have to height balance the tree. So if you draw an analogy of this with this, so this is your like 1 and this is this 4 part. So now you will have to pull this down. So if you pull this down over here, your binary tree is going to look like this. Now your left side was shorter. This is your left side or your left subtree which had a height of 0 and this had a height of 2. So you are pulling the tree down on this direction, like the direction which had the shorter height, and that direction was left. Hence it is known as a left rotation. So this is your height balance tree now, that is this is your 1 and this is your 4, and we assume here is your 2. Now algorithmically what is actually happening here, like pulling this down, like left rotation, whatever you call it, what is happening over here? Now in a basic node data structure you have 3 pointers. One is a pointer that points to the parent, the other points to the left child, and the third one points to the right child. Now let us note what were the pointer values in this tree. So the first node 1 is a root node. So the root node has no parent. So the parent pointer, now this P pointer means parent, LC is left child and RC is right child. So now P pointer will be null. It had no left child, so this would also be null and the right child would be 2. The next will be the node number 2, and this had a parent 1, left child is as usual null and the right child is 4, and this has that is node 4 has a parent 2, and since it's a leaf node both left and the right child values will be null. And now when you're pulling, what is happening is this 4 is just leveling up at this position, like it was at this tree it was at level 2 and here it is at level 1. Other than that no change has occurred. So the change actually occurs between the root node and the immediate left or the right child. So if it is a left rotation, as in this case, like this is getting pulled down, so the changes in pointers will be in the root node and the right child. So in case of left rotation it is root and right child. So let's look at the pointer values in this case. So here node number 1 now has 2 as parent and it becomes a leaf node, therefore no children. Node number 2, now this has a parent which is null and the left child is 1 and the right child it was 4 and it remains 4. And finally we have the node 4 which has no change. So essentially change happens here and here. So the parent gets changed and the left child also gets changed. Here also the parent value changes and the left child value and right child value both changes. Now if it had a node like this, say let us consider another node, say X. So let us just assume for some reason that we are going to height balance. This is an AVL tree, but for some reason we are going to assume that this is going to this is just for your information. So now if you have to bring this part down, So no change will come about in the left child. So left pointer will be the same, but the change is only in the right pointer. Like it will cease to have any right child. So basically change happens in the right child value and in the parent value. Here also the change happens in this value and the left child pointer value. So similar to left rotation, you also have a right rotation where now this is your root node, and on right rotation you are pulling this part down. So your 4 becomes a child of 2 and no changes is done in this particular node. So all the pointer values will be same. So only change will be done in this node and in this node. So root and the immediate right child in case of a left rotation and left child in case of a right rotation. So always we will rotate over the other side of the longer side, or we will rotate over the shorter side, in other words. And if the left subtree is longer, we need to perform a right rotation, and if right subtree is longer, we will perform the left rotation. Or in other words, we can say that if x side is shorter, then perform x rotation. So you can substitute this value with left or right. Now the change with binary tree, as you can observe here, is in binary tree the root was static, but in this case, since we are rotating, the root will always not be static. So these are the two basic rotations, left rotation and right rotation. So whatever be the value, you will perform either the right rotation or the left rotation. So let us take an example. So this is your tree. The right subtree has a height 1 and the left subtree has height 2. So now a new node is to be inserted in, which is to be inserted as the right child of this node R. Now this value is 3 and this is 1 and this is no longer an AVL tree. Now how to perform rotation? Do we start rotating at this point? No. We will always start rotating from the closest root to the newly inserted node. So the closest root to the newly inserted node will usually be, so this is the newly inserted node, so it will be the parent of the newly inserted node. So the parent of n is R and the parent of R is B, like this node. So the rotation will start at the parent to the parent. So the first rotation will start at this point. Now, though if you just consider this tree, this particular tree, this is a height balanced tree, this is AVL tree, like this is height 1, this is height 2, but we are going to perform a rotation because we want the height to be extremely balanced, like the maximum balanced, we like to bring about the most height balanced condition to this tree. So that's why we will be trying to first height balance, or we will bring the balance at this tree first, or the rotation at this tree first. Now since the left side is shorter, so a left rotation is to be done. So in the left rotation, so whatever changes will be done in these two cases. So this B and R. So R will be pulled up here and B will come down. So right now the node and the pointer table looks like this. So this stands for the null pointer value. So now when we are rotating here, so this part is fine, it was as it was. Now at this point R will come up and B will go down. So N was already there, so N will be here. B will come down as the left child of R, and since I was already a part of the right child, the left child of B, I will just remain where it was. So this is the first rotation. But is it height balanced? No, this is still not height balanced because still this has a height 3 and this is the height 1. So now what will happen is we will bring about the change to the parent of this node R. So there was the first rotation. After that, it just leveled up, and if you look at this point from the perspective of this node N, A is now the parent of its parent. So its parent is R and R's parent now is A. So you will keep on height balancing to the node which is the parent of parent. So now as you can see, you will have to perform a right rotation because this side is shorter. So now A will be pulled down. So this is the pointer values here. So this A and A in both the sides will be same. C values will be same. B values are changed, that is the parent node gets changed over here. Left child is same because it was left rotation, so left child value will be same, but there will be a change in the right child value. So it is null now, and it was previously R and now it's null. I will be same since nothing has been done to I. Now R has been changed because it was between B and R, the rotation, the massive rotation took place. So this was the parent, so a change in this value, a change in the left child value of R. So previously it had null, now it has got B. And this new node will have the same values in both the tables. Now let's try to rotate this over right. So we are going to perform a right rotation here. So now A and C is brought down and R is here. And since there will be no change, since we are doing a right rotation, no changes will be done to the left child of R. So now B and the left child of B will be same. Now what about what about N? N was the right child of R and now the right child of R is A, and since this is a binary tree, you can't fit in N anymore in R. So what happens is now N is brought down as the child of the left child of B. Now the question is, if you might say that what if B already had another child, another right child? But this will never be the case because since we already had rotated, so B was here, so originally R was the right child of B, and since we performed a rotation, R ceased to be a right child of B, and this pointer will always be empty, and therefore you can easily bring down N in this position and you can just fit in N at this point as the right child of B. So here a number of changes. So now A will change because rotation happened between A and R. So A will change naturally. B will remain the same because no change has been done to B. So R will change. So now it has a parent of null. Right child is A and left child is B, and some changes will also be done to N where the parent of N becomes B from R. So this rotation actually continues till the tree is balanced on both sides. So now see, this has a value of 2 and this side also has a value of 2, so the difference between them is 0. So naturally, in the next insertion, whatever be the node, wherever it be inserted, there will be no need of any rotation or any height balancing. So we try to actually balance this in a way that we don't have to balance a number of times. So every time a new node is inserted, we make sure that we don't always have to perform this kind of height balancing. So this is also known as a left right rotation, because first left rotation was performed and then a right rotation was performed. So this is known as a left right rotation. Similarly, if it had been the other case, like if this part was in this position, in the right position, and this new node had to be inserted at this position, we had to perform a right left rotation. So this is how a binary tree is height balanced in order to form an AVL tree. So the basic algorithm is like you insert or delete a node according to the binary tree insertion or deletion rule. Next, you will check the height difference between the subtrees, and you will find out that if height of the left tree is minus height of the right tree, the absolute value is greater than 1. So what is the absolute value? If you have an absolute value like say 3 minus 5, so 3 minus 5 is minus 2, but the absolute value of minus 2 is 2. So it basically ignores any negative sign and always returns a positive number as the difference. That is known as the absolute value. So now if it is no, like it is within the AVL tree height limit, then the insertion or deletion, like whatever, that is stopped. But if it is not so, then you will rotate the node from the closest point to the disbalance and move up the tree until the whole tree is height balanced. That is, the closest that is closest to the point of disbalance is actually nothing but the parent of the parent. So you will always tackle the parent of the newly inserted node, and now after it is height balanced, the insertion or the deletion method is stopped. So that is all about AVL tree. If you have any more doubts, any more questions, please do write to me about that. And that's all for today.